Let us now start our session on CAD to real world. Uh, there have been a lot of people who've been asking me under what conditions we use 2D drawings, under what conditions we use 3D models, and I want to give a brief over here on what kind of manufacturing processes require 2D and what kind of manufacturing processes require 3D. Uh, Quite often 2D or 3D depends on what kind of information you want to deliver and for whom you're delivering it. So let us take certain examples of different manufacturing processes and understand what the manufacturer expects as a designer, or rather from the designer. A manufacturer who has a conventional machine, be it a lathe or be it a drilling machine, a conventional drilling machine, which need not have any access or a computer control, quite often requires a paper in hand which talks about details of the design. This has to be a ready reckoner for them. Uh, it is extremely difficult if we end up giving a 3D model to these people where they have to go back to their systems, understand the material used, understand the fits, understand the tolerances. Rather, they would prefer having a piece of paper that essentially has all the details. So in such cases, it's uh, always advisable to have a 2D drawing which details all these aspects. This is a typical 2D drawing. If you see over here, it has all the information right from the basic dimensions of the components, be it the dimensions of the holes, be it the dimension of the exterior, or the material that is used for the component, or the raw material size. It also has details on who did the design and what the drawing number is. There's an area in this template which is generally used for version control. So for example, today I have the dimension of 20 mm here. So tomorrow if I want to make it 40, I can make it 40 and just give a version control over here saying I changed the dimension from 20 to 40. So this gives a good understanding to the manufacturer as well, or to people who continue with the design, to say why a change was made. So these drawings can also be generated through a 3D model, but you will have to ensure that you get a drawing with all the necessary details. A manufacturer that has access to a computer numerical control machine will be more than happy to have a 3D model. Quite often, these manufacturers use the 3D model to put it in their CAM software, which is your computer aided machining softwares, which generate the toolpath. Uh, Here, you'll have to give them a file which is in the format of STEP or IGS, simply because they might be using a 3D modeling software, which is quite different from the software that you use. So in such a case, it is important that you give them a common file that is accessible to both you and the manufacturer. So this is a 3D model that is shown here. Even though these manufacturers who have CNC machines use 3D models, quite often they would want a 2D drawing along with it, simply to understand the critical features of the component. Quite often in a 3D model, it's difficult to understand what kind of finishes you need, what kind of tolerances you need. So these aspects come in a drawing. So even if you're building a 3D model that the manufacturer uses to complete building the product, it is important that you generate a 2D drawing with all the necessary information, be it on the material, be it on the fits, be it on the surface finish, be it on the dimensions, the tolerances, the version control. It's a good practice to not only have a 3D model, but to have a 2D drawing at any point of time. One of the commonly used processes is also laser cutting. With laser cutting, we generally laser cut sheets. So quite often, people who use laser cutting machines will require a 2D file, a 2D drawing, preferably in a .dwg or a DXF file. This helps them generate a tool path to cut a sheet. Uh, so this is a typical drawing. You need not necessarily give the dimension details over here. Since it is a laser, it will just go by the path that you have shown in the picture. So as long as you're happy with the dimensions that you've given, you can go ahead and uh, cut them. Laser cutting is done on flat sheets where the path taken by the laser is generally on the XY plane. A very popular method today is 3D printing, simply because quite often you design something in the morning and you can get the part by evening. So this has become a very popular method, and frankly, a 3D printing model is is a very good uh, prototype building option where you can validate a bunch of assumptions that you have. A manufacturer who has a 3D printer generally will need a 3D model, be it in a .stl file or a .step file. So this is a 3D printer that we designed, my company, which is called Brahma 3. This is an FDM based 3D printer. So this machine is capable of 3D printing in uh, the machine that you see here is actually a machine that we designed and developed. It's the Brahma 3 Annual. It uses the FDM-based technology to 3D print objects in plastic. We'll talk more about 3D printing in our next session. So just to give you overall direction on when you use 3D and when you use 2D. 3D is it one, as I told you earlier, it depends a lot on how you're getting it manufactured. You need to have prior information of that. 3D is also commonly used as a communication while discussing the design. It's easier to imagine with 3D rather than having 2D drawings with multiple views. So now it's quite popular in team discussions where you have a 3D model and you start understanding what you need from it. 3D is also quite often used when you have to carry out software analysis, primarily to validate some of the assumptions you have. Like you saw earlier during the CAD session, where there was an analysis done on an L angle. So it gives us a fair idea of whether we have to add ribs, whether you have to increase the thickness. So 3D is quite often used for software analysis. 2D is used to give clarity of information pertaining to the design. It's extremely difficult to give this in a 3D, especially if you have to talk about the surface finishes, talk about the material, talk about uh, the fit, talk about the clearances. So 2D is a common method, and it's definitely a good practice to have that you generate 2D drawings from 3D models or directly go with 2D drawings. So this is some of the thoughts that I had on how you could use 2D and 3D to your advantage. What we'll now go ahead with is starting the session on 3D printing. This should give you a fair idea on how you can get your designs to life. So this session will be handled by Santosh. He's the founder of Xdroid, and he built his own 3D printers as well. So over to you, Santosh.
My name is Santosh. I'm the founder of Xdroid Prototyping Technologies. This company was founded in the year 2017, and it was completely based around my passion for 3D printing. I am here today to kind of give you guys an insight into 3D printing and the complete world of this technology, and kind of introduce you to how much humanity has developed in this domain. So, in this regard, I would start with the presentation. Okay, so first of all, 3D printing comes under the category of additive manufacturing. All right. So additive manufacturing, as the word signifies, is additive in nature. So the kind of manufacturing techniques you would have heard to date are mostly subtractive in nature. So what this means is that you have a block of material. This material could be wood, this material could be metal. You're going to remove material to kind of get the shape that you want. And this is how additive manufacturing, right? It's a lot different from subtractive manufacturing. And that's why it also gets the name additive manufacturing, because you're going to take a material, and that material could be literally anything as long as there is a science to combine it into an object. Now, additive manufacturing kind of starts from nothing to something, and that is why over time it has also been called 3D printing. Okay, so the current 3D printing techniques, right, they are based around the principle that every object in the universe is nothing but a slice of two-dimensional planes. So to explain this to you, I would kind of want to give you a gist on, the whole geometry of the universe, right? So everything in the universe starts off as a point. Now, if you were to arrange points, collinearly, they would form a line. And if you arrange lines collinearly, they would form a plane. And now when you extrude a plane, you get a solid. And if you're going to extrude a solid, it's again only going to be a solid. So three-dimensional is the ultimate. So based on this concept, right, 3D printing also uses the deposition or uses the combination of layer upon layer upon layer to kind of build the 3D part. So that is why it is commonly known as 3D printing. And because you're going to build something from nothing, you absolutely have no geometric limitations whatsoever in the part. And you don't have to essentially create new tools according to the geometric complexity of the parts. Now, to kind of give you an analogous variation to this is that suppose you were going for CNC machining, right? Subtractive manufacturing of certain complicated metal objects, right? So when you have a really complicated radius or you have a really complicated geometry, you will have to create a tool specifically to make that part. And that adds time and cost to the entire process. So this is where 3D printing is not only technologically dominant, but technologically a better alternative, but is also economical at the same time, and especially when you have to make a single prototype. So the whole point of additive manufacturing is that it takes the classical design for manufacturing concept and completely sinters it into manufacturing for design. To give you more clarity on this, let me give you a case to case example of an everyday life as an industrial designer. Okay, as an industrial designer, I am constantly making my designs according to the manufacturing tools, according to the manufacturing methods that are available in my geographical region, that are available to my budgetary requirements, that are available to my clients' budgetary needs. So even every aspect of the design, I am forced to compromise. I am forced to kind of crunch it into something that fits everything technically as well as budgetarily. So 3D printing gives me that leverage where I do not have to spend a lot of time. I do not have to compromise on a lot of the design requirements. I do not have to compromise on the fact that I cannot be so different from my competition in terms of my design. And kind of giving you all of this, just I'm trying to convey to you that 3D printing really helps with making the most complex designs, making your most original designs come to life with the least amount of effort possible. So this opens up new chapters for you to manufacture completely for design rather than design completely for manufacturing. So if I am kind of clear, I would like to move on to the next slide. So 3D printing has a lot of technologies and a lot of techniques, and we have a list here that I will run you through. And these are some of the most amazing techniques I have come across as well, and they fascinate me to this day. And believe it or not, these techniques, they started way in the 80s and they still hold good and they still are being used very much in different parts of the world for different kinds of applications, whether it be marine, whether it be aerospace, whether it be medical, according to the requirement, according to the need, according to the intensity or gravity of the application. we use different kinds of methods for 3D printing. Now, to start off with, let us start off with the SLA process, or the stereolithographic apparatus. All right. I would like to spend quite a few minutes on each method to kind of make you appreciate at the end of the day what is really amazing about these 3D printing technologies. Now, to start off with SLA, okay, SLA is the short form for stereolithographic apparatus. It was patented and it was kind of invented by a great person by the name Charles Hull. And he was the co-founder of 3D Systems Inc. Now, this is the oldest known method of 3D printing, and in fact, much before the whole jargon of 3D printing came to be, SLA or stereolithography was probably the only name people would talk about. Kind of like how we speak about Xerox today. You want to photocopy a paper, we go around saying you're going to Xerox, you're going to Xerox. Kind of that was the time when people were like, if you wanted to 3D print something, they would go around saying, are you going to do stereolithography, are you going to do stereolithography? So this is where SLA came to be one of the first and oldest methods of 3D printing. Now, to give you clarity on the process of this 3D printing, I would like for you guys to focus your attention on this image on this slide. Okay, so you have a container, and this container is filled with a liquid plastic. Okay, these liquid plastics are kind of thermoset in nature. They come under the thermoset category of polymers, and they also fall under the category of photopolymers. Okay, to tell you what photopolymers are, these are polymers that get cured under the action of light, meaning they are always stored in dark containers. They kind of work the same way developing fluid works in the photography industry. If you have seen movies, if you've seen a developing room, you will notice that the silver based liquid is always done in a dark room, is always used in a dark room, because this liquid tends to react with light, correct? So similarly, this container or this vat that is filled with the photopolymer can easily react with light. So that makes it a very good applicator for this 3D printing process. Now, there is a platform, okay, and I hope you can see my mouse cursor. Can I just have that acknowledged? Can you guys see my mouse cursor?
Yes, sir.
Okay, all right, thank you. So you have a container, all right, and you have a platform. Now this platform is shown to be down with an object. Now to just give you more clarity, all right, this platform, all right, this blue layer, it is on top. It is very much on top, and this surface and the surface of the liquid, right, they are going to be the initial positions of the 3D printing. Okay, now as I told you, in 3D printing you have to join layer upon layer upon layer. So it does not mean that you are going to cut you know um, an object into indefinite number of layers. You are always going to cut an object into a definite number of layers. You are going to know the number of layers that the object is going to be made of beforehand. And you do this by finalizing or by deciding the height of each layer. All right, just to give you a clarity, if I were to make a 25 mm by 25 mm by 25 mm cube, all right, so I will say that each layer is going to be 1 mm in height, meaning I will have 25 squares which measure 25 by length and 25 by width, and I will stack 25 of these squares one on top of the other to get the 25 by 25 by 25 mm cube. Right, so this is the basis of deciding dimensions for your 3D printed part. Now, coming back to SLA, you have this platform which is on top. All right, Now this platform moves down the height of the thickness of the first layer. Okay. Now let us just say we are going to make the 25 by 25 by 25 cube on this. So if each layer is going to be 1 thick, this platform will drop down by 1 right? And when it does so, naturally the platform is going to get flooded with the photopolymer, correct? So we can say that the photopolymer has also formed a layer of 1 height on this platform. Okay. To continue the process, we have a laser on top. Now this laser is capable of throwing concentrated light, right? Laser is nothing but a concentrated light. It throws the concentrated light on the photoresin and then cures it. Now, if you have to make the same 25 by 25 by 25 cube, what the laser is going to do is simply draw a 25 by 25 square and then kind of fill it or kind of like paint inside the square. So wherever the laser touches the photopolymer is naturally going to get hard, or it is going to form a rigid object. The parts where the laser does not touch the photopolymer, it does not cure. Okay, so this way the first layer, or the 25 by 25 cube, or sorry, the 25 by 25 square is going to be formed. Once this square of 1 height, 25 across length, 25 across width is done, the platform moves down by 1 okay, and the process is repeated. And as you guessed it, the next layer will coincide. The position of the next layer will coincide with the position of the previous layer. So one layer literally gets formed on the next layer, and on top of that, and on top of that. So this platform moves down the height of 25 or this platform moves down 25 times to kind of give you that 25 layers that are going to be formed on that cube. Now, as you can see, there is a vase over here. Alright, I have given you something, I've given you an object whose cross section is literally concentric, or I'm sorry, literally symmetric along each layer. But if you can see this shape, right, if you can guess the cross sections, at least from the bottom to the top, right, you are going to have circles upon circles upon circles of different diameters. It's going to be small and then it's starting to become big. Ultimately, it becomes really big and then again it starts getting small. And then you have circles of the same diameter all the way until here, and then you have circles that are kind of increasing gradually until you form the brim, or you form the top layer of the vase. So once this is done, once the print is done, the laser is switched off, the platform comes up, and then you take the part out. That is it. So ultimately, this part is, it is a green part. It is, when I say green part, it means that it is going to be significantly soft and not very easy to handle by hand. So you need to be really careful because it might be really soft. So to kind of give the part some amount of rigidness for daily use or daily application, or for even using it or touching it, this formed object is then rinsed with a solvent and then placed under an ultraviolet light for a couple of hours till the photopolymer cures fully. And unlike the laser light, the ultraviolet, you can say, completes the process of converting the photopolymer into a full rigid solid. Okay, so this is the SLA process, and it is one of the most fascinating processes uh, I have come across in the 3D printing domain. Right. So moving on from SLA, let's move on to digital light processing. Okay. Now DLP is very similar to SLA under the guise that it also makes use of photopolymer. Now by now you must have guessed that a 3D printer or a 3D printing technique requires two things. One is a material and second is a science to kind of combine that material or form an object or a solid out of that material. Now, the material could be either a liquid, it could be a plastic, it could be a hard plastic, it could be a powder, it could be anything. And the management of that material varies across different 3D printing techniques. Now, for SLA and DLP, we are using liquids, and liquids can always only be stored in containers, right? So the work holding device or the work holding mechanism is simply going to be always a vat or a container. And the process of the process of working or curing this photopolymer will require additional mechanics. And this mechanics can kind of change according to the way you're going to process or way you're going to draw the layer or the cross section on the material. Okay, now to continue with DLP, so DLP stands for digital light processing. Okay, so DLP is very similar to the projectors that you will see in meeting rooms and offices. You must have seen them in colleges and schools. We obviously know the application of DLP. It is used to kind of project a computer screen or project some kind of an image on a wall, right? So DLP method is used to cure photopolymers into into solid to kind of do the DLP 3D printing. And to kind of explain this whole process to you, I will again kind of point out with the cursor. In this method, you have the vat again, okay, the container, and it is filled with the photopolymer. And as I told you before, the photopolymer is liquid and it gets solidified under the action of light. Okay, next, you have a light source from the bottom of the vat, meaning this vat's bottom, right, the bottom surface is transparent, so that it lets light to pass through it. And unlike the previous process where the platform was on top, in this method, the platform is at the bottom. It is over here. Okay. Initially, the platform goes up the height of one layer, and naturally, liquid starts flooding in this gap that is created with the action of the platform leaving a gap equal to the thickness of the layer. Okay. And then you have a DLP projector that is placed just under this vat. Now, the whole idea of using a DLP is that it is a great source of heat and light. If you've ever placed your hand next to the projector, or if you've ever placed your hand against the light that is being projected by a DLP, you will notice that it has some amount of temperature to it. And it is also a great source of light, and not just any light, but of an image. Okay, so what the DLP technique does against the laser, okay, is that in the laser method, right, under the, let me just go back to SLA. So in SLA, this laser is required to draw the perimeter of the cross section as well as fill that cross section. But in the case of DLP, it is going to simply project a black and white image of the cross section. Okay, wherever it's basically an image with a black background, and the cross section is in white color. So to kind of give you better clarity on this, black is equal to no light and white is equal to light. Okay, so wherever there is black, this photopolymer will not act, and wherever there is white, that is, it forms the geometry of that cross section, the photopolymer will become hard. Okay, and then once the first layer is formed as a result of this DLP projecting that cross section, this platform again moves the height of one layer, and then it projects the cross section of the next layer. If you were to guess how this vase was formed, right? So this circle, right, with this diameter was first projected. then the platform goes up, and then this circle is projected, and then this circle. So after every projection and after every curing of the photopolymer, a new layer is formed in the DLP process. And subsequently and over time, layer upon layer upon layer upon layer gets formed in the reverse direction for the object to be formed. Okay, so this is the DLP method, and the resin in this case kind of hardens very quickly because there is a huge amount of light that is being projected against, using lesser amount of light as compared to SLA. All right, so this is the SLA process. And let me just kind of, because these two categories of 3D printing come under the very similar divisions of 3D printing, I would like to say that in this method, right, the laser is able to move on the X and Y direction of the coordinate space, while the platform moves along the Z direction of the coordinate space. Now, in the DLP's case, the X and Y coordinates are directly determined by the cross-section itself, and the platform moves along the Z-axis. And for this platform to move up and down, you have a motor connected to perhaps a screw rod or any similar kind of a drive system to move the platform up and down. Okay, so this is SLA and DLP, and both of these methods use photopolymers. So having said this, I will move to the next method, which is fused deposition modeling. Okay. Now fused. Can I continue? Okay. So the next method is fused deposition modeling. All right. So fused deposition modeling was significantly the most it is significantly the most popular 3D printing technique that is used across the entire world. Okay, it was developed by Mr. Scott Crump, and he founded a company by the name Stratasys in the 1980s. So Scott Crump and his company owned the patent rights for fused deposition modeling until 2000, until the year 2000, post which the patent lost its technological, you know, this the patents, they basically hold a technological validity beyond which new technologies are set to kind of replace these. So that is the reason patents are given a lifetime of about 12 to 20 years. Now, under this same window of things, Scott Crump and his company has also had the patent for FDM until the year 2000. And after the year 2000, people started kind of open sourcing the whole fused deposition model technique. And that is the reason, even to date, it is very simple and very accessible for anybody, even at a college state or a college level, to build and own an FDM 3D printer of their own. Okay, and because of certain copyright methods, copyright difficulties, a lot of people could not use the name FDM for their 3D printing or for their 3D printing methods, which is why a lot of companies that kind of started using FDM to do 3D printing later on were forced to use the word or the jargon fused filament fabrication as against fused deposition modeling, because Stratasys kind of used it as their unique selling point. Now, unlike the SLA and DLP methods, okay, this is the only technology that uses production grade thermoplastics. So now I hope you guys are very well aware of the difference between thermoplastics and thermosets. As you know, two of three classifications under polymers. I mean, you must be aware that there's thermoplastics, there's thermoset polymers, and there's elastomers, or what you find in rubber bands. That is nothing but elastomers. Now, thermoplastics, all right, unlike the thermoset polymers, are always existing in their solid state. Okay, these thermoplastics are not capable of lasting or existing in a liquid state or never in a gaseous state, because what makes them different from the other plastics is that the moment they are made to reach their liquid state, the polymer is not a polymer anymore. Just to give you a very brief science, in school, you guys must probably remember that a polymer is nothing but a chain of monomers, or it's nothing but a chain of molecules, right? So this chain of molecules is a simple physical chain and not a chemical chain. And this chain can be weakened under the action of heat, and it can be broken with the complete action of heat. So that is the meaning, I mean, that is the reason thermoplastics can never exist in their liquid state or their gaseous state. Okay, so if you guys obviously remember that from solid to liquid you have something known as a melting point, and from liquid to gas you have something called a boiling point, right? So thermoplastics also have some kind of a melting point beyond which they don't become liquids, but they depolymerize. So once they depolymerize, the individual molecules of the thermoplastic separate, and you will not be able to use this material like the thermoplastic itself. So to give you an example of a very commonly used thermoplastic is your water bottles, or your Bisleri Aquafina bottles. Those are called PET, or polyethylene terpolymer. So it is basically ethylene terpolymer, a chain of those molecules to form the PET material. Now, if you were to burn this bottle under the action of heat or under the action of fire, you will notice that it just melts away. It simply melts away. You will not get a liquid form or a gas form of this plastic. All right. So keeping all of this science in mind, I would like to tell you how this science is significant to this 3D printing technique. Okay. So now, as the other slides, I would like to get you guys to focus on the image on the slide. Okay. In the previous case, we had liquid that was stored in a vat, but in this case, we have a thermoplastic in the form of a wire. Okay, you can see something called the material spool over here. This is basically like a bobbin. Okay, kind of like what you see thread in a tailoring shop, a thread that is wound around a bobbin. You have plastic wire of a definite diameter, and this diameter is about 1.75 mm. It's a little invariable to this discussion, but it's just important to know that this diameter is constant for the entire wire. Right, so you have this plastic spool over here that is stored or that is kept just next to the machine, and then this spool is pulled out and fed into something called the heater element. All right, the heater element consists of a throat. Okay, and on the top of this throat, action number 1 happens, and at the bottom of this throat, action number 2 happens. Now, action number 1 consists of 2 rollers, as you can see here, which is actuated by means of a motor to kind of push or pull this wire to or from the nozzle, or the other side, or the second action, where the heated plastic, right? So once this plastic is pushed down through these rollers, they get heated in this area, and they become, or they go to something known as the glass state or plastic state. Okay, that is basically that once they are heated up to a certain temperature, they become soft. So when they become soft, they can be made into any kind of a shape, and upon cooling, this plastic will hold that shape. Okay, so when these rollers push this wire, they go through this heater element. They are heated up to that plastic or that glass state, and then they are extruded out through this nozzle. Now, this This wire, okay, in general machines, it has a diameter of 1.75 mm, as I told you, and the nozzle could be anywhere, between zero point 0.3 to 0.4, zero point 0.5. You have up to 1 mm nozzles as well. But typically, we use 0.5 mm as it is a very convenient extrusion diameter. All right. So in this method, what happens is that the liquid plastic, I'm sorry, not the liquid plastic, the molten plastic, right? The melted plastic comes out of this nozzle. And as you would have guessed, this platform will initially be against the height of this nozzle. Now, this nozzle is able to move in the XY direction, and the platform moves on the Z direction. So first, what the nozzle does is, let us take the same example of the 25 by 25 by 25 cube. Okay, so the nozzle will draw the first square, that is 25 mm along length and 25 mm along the width. Okay, and then fill this square with plastic again. Now this plastic will have a certain layer height. Okay, then the platform drops down the height of this layer, and then this nozzle again interpolates the xy square, or 25 mm square by 25 mm square, and fills it up. So subsequently, this platform moves down 25 times, considering that the height of each layer is 25 mm, right? I'm sorry, the height of each layer is 1 mm. So you will kind of have 25 layers, 1 mm thick, to give you the ultimate part, which is 25 mm along length, 25 mm along width, and 25 mm along height. And in this method, the nozzle and base are built to accurately move in their corresponding directions. Okay, and the best part about the FDM methods is that the parts that come out of this process require little or no post processing. You might want to do post processing, or you might want to finish the part only if you had certain uh, significant changes that you would want to do to it aesthetically, but performance wise, these materials are suited for certain static applications. Okay, when I say static applications, it means that the part will not be under any kind of moving or dynamic loads. Okay, so if they are to go under the applications where you require dynamic loads, this plastic will have to be infused with different kinds of reinforcing material, and then perhaps according to the application they can be suited for dynamic loads as well. Okay, so I will run you through a small demo of the FDM process towards the end of this presentation. Okay, so concluding FDM here, I would like to move on to the next method, which is selective laser sintering. Okay, so across the three 3D printing methods that we have done till now, the first two methods used liquid. Okay, the third method used solid. And what separates SLS from the other three methods is that it is going to use powders. Okay, now, it is very interesting to know how you can combine powder into a solid, and that is exactly what selective laser sintering does. Okay, so as the name signifies, okay, you are going to use a laser. Okay, let me point this out. You are going to use a laser to selectively sinter powder. Okay, what it means is you're going to sinter powder, and the process of combining powder together to form a lump or to form a mass is called as sintering. Okay, to kind of give you a macro explanation of sintering, imagine you had a lot of spheres, okay, and you arrange these spheres one on top of the other. If you were to spot weld them, okay, they would form one complete object. So sintering is analogous to spot welding powder together to kind of form the part that you want. and you are able to sinter certain powders selectively by the action of laser. Okay, to kind of give you a very brief history back on SLS, it was developed by Carl Deckard, who was a student at Texas University, and his professor Joe Bayman. And this happened in the year 1980. Okay, and we are going to be using a very high-powered CO2 laser to perform the SLS method. Okay, so now I'd like to divert your attention to the picture again. Okay, so to start off, you will have a laser and a mirror. The laser is basically a source, and this laser is focused against the print body. Okay. Now, to give you better clarity, you have two platforms in this method against a single platform being used in the last three methods. Okay, so these platforms are called the reservoir platform and the build platform. Okay, and as you can see these directions, this platform will move in opposite directions. Okay, to start off, this build platform has its surface right on the top, and this reservoir platform has its surface right at the bottom. Okay, so you're going to have some amount of volume over here, and you're not going to have any volume over here. Okay, the idea over here is to push this platform up the height of the layer. Okay, first, this platform having the empty space or the empty volume is filled with unsintered powder, or it is filled with simple powder. Okay, now the material of this powder could be anything from plastics, it could be ceramics, it could be a glass powder, it could also be to an extent certain simple soft powders like aluminum, it could also be certain grades of steel powder or silver powder. Okay, all of these powders are capable of getting sintered under the action of a CO2 laser. Okay, now in this platform, you have the powder. Okay, and this platform moves up the height of one layer. So naturally, what's going to happen is at this surface, an amount or a volume of powder equal to that height is going to get displaced. Okay, and then this platform which is on top will move down the height of the height of the same amount of volume. Okay, basically the powder that gets displaced over here is equal, or the volume of powder getting displaced over here is equal to the volume that is created over here as a result of this platform moving down. Next, what happens is that the roller pushes this displaced powder from this platform onto this platform and forms a layer whose height is equal to the height of the object. Okay, now once this step number 2 is completed, the laser, okay, which is capable of moving in the XY direction, draws the cross section of the first layer and fills it. Okay, this is the third step. This is the three-step process by which the SLS process happens. So just to run you through, step number 1 is to put some amount of powder to get displaced. Step number 2 is for this platform to drop down and this roller push this powder from this platform to this platform. And then step number 3 is for the laser to move in the XY direction and form the layer. So this three-step process happens 25 times, as in the case of our 25 by 25 by 25 cube, to form the 3D printed object. Okay, and I'm sorry, I forgot to mention to you guys that the CO2 laser is capable of, sintering this powder or spot welding the powder and form the layer or the 3D printed part. And as the previous methods, as like DLP or SLA, where you have a photopolymer and that photopolymer cures only in those selective spots where the light acts, right? Similarly, even in the SLS method, wherever the laser touches the powder, those are the parts that are going to get sintered. So in this method, one of the greatest advantage is that if you have a part who has which has an overhang, okay, something like a cantilever, this will not pose a problem. To kind of give you a, a clarity on what I'm trying to explain over here, imagine you have a part which is in the shape of an opposite L. Okay, so if the shape is an opposite L, you're first going to create the vertical column and then you're going to create the horizontal column. As 3D printing always involves putting one layer on top of the other layer on top of the other layer, you naturally can guess that each layer supports the subsequent layer, right? But in the case of our reverse L, the moment it starts drawing the horizontal column, there is a portion of that horizontal column that does not have the support of the previous layer. So naturally, if it is a liquid or if it is a plastic, you can guess that it's going to be a breaking point, right? And the plastic might just fall off over there. So for that reason, in the other methods, we use something called temporary supports. And these are again 3D printed temporary supports which print along with the part. They are very similar to the scaffolding that you will find when a newly constructed building is kind of being done. Okay, when they're creating the ceilings, right, the ceilings above you, and they have to lay the bricks, they need a support, they need a scaffolding to lay the bricks on for the bricks to set, and then they can remove the scaffolding, because failure to do so would be impractical, it would be unrealistic. You would have no means for that brick to kind of just hang in the air, correct? So that is the reason you will be using supports. Now, the reason I explained this much to you is in the case of SLS, because the entire volume is always filled with powder, okay, the powder itself is able to kind of support different kinds of overhangs. So if you can see this small extension over here, or if you can see this extension over here, there is a certain degree up to which these methods will also not require supports, because each layer is kind of able to form a draft or an angle up to which it can to an extent support the cantilever. But then if the angle is too extreme, right, something like 5 degrees or something typically less than 30 degrees to the horizontal, right, those kinds, 20 degrees or 30 degrees to the horizontal, those kinds of parts require a support. And in the case of SLS, you require no supports whatsoever. Okay, so next we will move to SLM. Okay, so SLM is very similar to SLS. Okay, so I will kind of run through SLM because I've explained how the SLS method works. Even in this method, you have a build platform and a reservoir platform, but SLM is very specifically used only for metal powders. Okay, and there is a reason for using SLM for metal powders as against using SLS for metal powders. So as I told you in the previous method, that SLS is very analogous, or SLS is very similar to spot welding powder particles together. SLM goes for full melting of the powder to form a cross section. So for this reason, you have a very powerful high wattage laser that literally melts the powder, up to, it takes it up to its melting temperature, crosses its melting temperature, and melts the powder into the cross section. And as you guessed, again, you're going to have this platform move up the height of one layer, this platform move down the height of one layer, the roller moving the powder, basically displace powder from here to here, and then the high wattage laser kind of, you know, melts the powder, not just simply sinters it, melts the powder and forms the cross section. So over time, you are going to have a cross section of this part, okay, that is getting stacked layer upon layer upon layer to form the part. And this method, okay, it creates something known as a green part, okay. And in industries, in mechanics, when we say green part, it means that the part is not fully formed internally. The lattice structures and the lattice bonds of the part are not developed fully, and for this reason they have to be heat treated in an autoclave for a couple of hours, before which they can be deemed as usable for applications. Okay, now SLM uses a lot of powders, and these powders could vary from stainless steel, you could use titanium, you could use aluminum powders, Inconel powders, and a lot of industrial grade powders. And the really nice part about selective laser melting is that this method can create parts that you can directly use in industrial applications. To give you an example on that, a lot of parts on the SpaceX program and the SpaceX rocket, a lot of the nozzles and a lot of components that go inside the rocket are 3D printed. And even if you have not heard a lot about SpaceX using 3D printed parts for their applications, you must have very well heard of the the automotive company by the name Bugatti. So Bugatti uses 3D printed brake calipers on their cars. Okay, and these are completely done by the selective laser melting method. They are fully made using 3D printed. They have a geometry which cannot be machined even with 4-axis, 5-axis CNC machines, and they are being used on production grade cars even to this day. Okay, so that is kind of just to give you a clarity on a real world application for selective laser melting. Okay, so I hope that you guys have been following until now, and it having said that, I will move to the next method, which is polyjet. Okay, now you can imagine polyjet method, all right, to kind of be a combination of what we learned or what we came across in SLA and digital processing with the motion mechanics of fused deposition modeling. Okay, it's kind of a technique that combines the best of these abilities. Okay, so in this technique, you again imagine a platform which can move along the Z direction, and a print head or a head that kind of deposits a material on this platform and is able to do so in the XY direction. All right. So unlike FDM where you have a plastic wire, in this case you have a resin tank, and as you guessed it, this resin tank contains photopolymers. And to give you a recap on the photopolymers, they are polymers that get cured under the action of light. Okay, so you have a platform and you have a kind of print head which is very similar to the inkjet head that you use for printers at homes and offices. Okay, and this print head is capable of spraying a very small or brief amount of photopolymer and immediately throw light on these to cure that photopolymer. So technically, you are going to spray small droplets of photopolymer on a platform and then cure them immediately, forming the layer immediately or the cross section immediately. Then the platform moves down the height of one layer, and then this printed again sprays the photopolymers on top of the previously done layer and cures them using the lights. So over time, the same ways, right, that you saw. So you have it starting from this cross section, cross section, cross section, going layer upon layer and creating the part. And now the difference between this method as compared to let us say FDM and SLA or DLP, is that the parts come out perfect. I mean, almost very one-to-one geometry wise. In the case of fused deposition modeling, although the method is very simple, you may notice that there is a lot of steps or a lot of layers that become too significant for the naked eye. But in the case of polyjet, these uh, this 3D printing technique creates parts that are, you know, very perfectly done geometrically, and this finds very good applications in fluid dynamic and wind tunnel testing, to be very specific. To kind of give you an example, across 2016 or 2017 to be more clear, I did a part known as pitot tube for military application. Okay, so there was a helicopter being developed uh, by our own Indian organization, HAL, and one of their ancillaries was tasked to develop a prototype of a pitot tube, which they could use in their wind tunnel to kind of test out a certain degree of parameters. So at that time, we deployed polyjet technique to create that pitot tube and give it to them for their wind tunnel testing. And because polyjet creates parts that are equal to injection molding, they are equal to the geometry that you would expect out of a production grade part, right? Polyjet becomes very extensively used in such mobile and such good applications. Okay, so this is the polyjet technique. Okay, next I'll move to electronic beam melting. Okay, now EBM was developed by or coined by Arkham AB. Okay, very much in the year 2000. Okay, now EBM is very similar to selective laser melting. Okay, but I will tell you what the very significant difference between selective laser melting and electron beam melting is. Okay, so both of these methods are used primarily for metal powders. Okay, and both of these methods involve complete melting of these powders. And the difference is, in selective laser melting, okay, in selective laser melting, where you have this laser kind of interpolating along the XY direction and the platform moving along the Z direction, EBM uses the same kind of projection that DLP uses to project the cross section of the layer on a platform. Okay, so you don't have two platforms in this case where you have a reservoir platform displacing powder onto a build platform. No, you just have one build platform, okay, which is filled with powder. Okay, and this powder is fed using a powder feeder, and then you have an electron gun that kind of projects the entire cross section of the layer all at once. Okay, so once this powder is fed and the electron beam is done at the same time, the powder kind of forms or melts to form that cross section, okay, or that layer. And then the platform moves down the height of one layer and the process starts over again. So subsequently, you are going to get a part which is not only more higher grade finish than SLM, but which will also be very significantly more dimensionally accurate as compared to selective laser melting. I mean, I should say that both SLM and EBM methods will definitely form green parts and will require autoclaving later. But the amount of machining or the amount of correction to dimensioning that you will do on EBM is far lesser than what you will be doing to correct a dimension out of a part created by the SLM process. And if we move on in the future to the days where we will be replacing conventional metal metal manufacturing with SLM and EBM, with a number of machines, right? So when you're creating each part, if you are going to spend, say, 10 minutes to correct the dimensions of a part created against SLM over 8 minutes that you would be doing to correct the dimensions of a part created by electronic beam melting, you're going to save 2 minutes per part. And if you are going to create about 1 million parts a year, you are going to save 2 million minutes that year, 2 million production minutes, which is a lot of production time, which can make a lot of significance towards the goals and the kind of revenues and objectives that are generated and accomplished by an organization that uses EBM against the selective laser melting method. Okay, so lastly, we have laminated object manufacturing. This laminated object manufacturing is one of the most interesting, really, really interesting 3D printing techniques. Okay, and it was developed by a California-based company by the name Helicis. All right. So I would like to get you guys to focus on the image again. Okay, unlike the previous methods that used a powder or powder in the case of electron beam melting, SLM or SLS, or liquid polymers, right? The photopolymers against polyjet, DLP, and SLA, or the plastic thermoplastic wires in FDM, right? LOM or laminated object manufacturing does not use material that looks anything close to the other methods. And the reason this is called laminated object manufacturing is because it uses a sheet, right? A sheet or a laminate that starts off from a supply point up to an end point. Okay, so you have this first coil. This coil starts like this. The coil moves against the platform and then recoils into a part. Okay. Now you might wonder where the magic happens and how the magic happens. I will be sure to give you that clarity. So what is over here is a complete foil. All right. And what is collected over here is a waste foil. Okay. Please don't think that there is nothing that is being done to this foil. All right. So even in this case, you are going to use a mirror and you are going to use a roller. Okay. Now, to start off with this process, I'm going to tell you that this foil consists of a laminate. All right. And this laminate sheet has a thin layer of adhesive on top of it. And this adhesive could be either on top or it could be at the bottom. It doesn't matter. Okay, so this laminate sheet moves up and against a heated roller. Okay, now the job of this heated roller is two. The first job of the heated roller is to form tension against this overhang. And the second job of I'm sorry, there are three. All right, I'm sorry, it wasn't two, it was three. So the second job of the heated roller is to push the the laminate. And the third and most important job of the roller is to heat the laminate and activate the adhesive that is there on the foil. Okay, the moment this adhesive is activated, okay, where the adhesives, wherever the adhesive touches the platform, it gets stuck. So in the case of the first layer, imagine that the platform is at this height. So the roller heats the laminate and it activates the adhesive. Okay, immediately a laser is used to cut out the cross section and fill that cross section. Okay, it basically cuts out that cross section. It necessarily does not even fill it. I'm very sorry for having mentioned that. It just simply cuts the cross section, and this cross section gets adhered to the platform due to the activation of the adhesive. Okay, then the platform moves down the height of one layer, and then this roller moves a new fresh layer of laminate on top of this, and then the laser cuts the next cross section, and because the adhesive has been activated, that cross section gets stuck to the previous cross section. Then the platform moves down again, and the roller moves a fresh layer of laminate. And then, because the adhesive is activated and the laser is going to cut out that cross section as well, you are going to get layer upon layer upon layer upon layer, which is nothing but your laminated object layering or laminated object manufacturing. So this is the um, this is what laminated object manufacturing does. All right. So if any of you guys have any questions with these methods, I think I will give you guys about a minute to if you have a doubt, and I will move on to the next part if that's okay. So I'll give you guys a minute to kind of think about any questions you guys have. Okay, I think I'll just move on to the next slide. So the next slide is basically to tell you what the whole 3D printing process itself is. Okay, so previously we came across about 8 methods of 3D printing. Now the magic is that all of these 3D printing processes require some amount of steps that need to be done, that need to be deployed, regardless of the kind of 3D printing method that you will be doing. Okay, so I would like to start off with saying you will always and always require a CAD model, okay, a computer aided design model on the computer, which could be something you made, it could be something that someone else made, it could be something you found or downloaded from the internet. You will always and always need a CAD model. Okay, to give you good clarity on the 3D printing process, I will make this slide analogous to what you would do to print a simple document on a sheet of paper. Okay. Now the 3D CAD model is analogous to the document you might have on Microsoft Word. All right. So this document, again, it could be something you created, it could be something someone else created. It is natively in the software that you created it on, and it is easily editable. All right. So the next step with the 3D CAD model is to put it in something known as a printable file. Okay. This is analogous to converting your document into a PDF. And the reason for doing it into a PDF is, firstly, you don't want anyone to edit your files. And secondly, you must notice that sometimes you created a certain degree of orientation, a certain degree of structuring your document and the line spacing and the different aspects on your document the way you want it to turn out after you print. But in some cases, because of certain photocopy shops or some places that you go not having the same version of software as you, this orientation or this structuring tends to change, and that is not good for you, right? So that is the reason you go with a PDF file, and it's a protected file. So for that reason you use the printable file, which is basically converted from the 3D CAD model. And in the case of documents, as it is called uh, PDF, in the 3D printing process, this printable file is called an STL. Okay, and STL basically is nothing but a three-dimensional mesh of the object. Okay, and STL stands for Standard Tessellation Language. to kind of give you an example of what happens over here, I will just stop sharing this screen and I will show you day-to-day application of this STL method. Okay. So here I have my CAD software. I prefer using Autodesk Inventor. As you guys can see this part, all right? So this is a part that was created at a time of the COVID-19. It is a respirator part, all right? So this is some part that kind of has been created on this CAD model file. I mean, sorry, this CAD software. So what I will do is go ahead and convert it into an STL. Okay, so my software will convert this into an STL. Okay, now what an STL is that it is a three-dimensional mesh. Okay, and to kind of give you what clarity on what this mesh looks like. Okay, this mesh is nothing but a mesh of triangles. Everything along this mesh is a triangle. You can see the different triangles. I'm not able to point them out at you. Probably this is one triangle, this is another triangle, this is another triangle. They could be triangles of different forms or different sizes. They need not necessarily be equilateral triangles. They need not be significantly looking the same. All right. So this is known as an STL file. Okay. So what I will do is save this STL file somewhere on my computer. Okay, I can just simply save it on the desktop, or I will just simply save it on any drive. Okay, so this is all I have to do to kind of convert a 3D CAD model into an STL file. And then what I will do is take the STL file and put it in something known as a slicing software. All right. So to show you what the slicing software looks like, all right. So this is called as Cura. It's one of the slicing softwares that we use to do the FDM 3D printing. All right. So I will first load the file which I converted into an STL. Okay. So in this process, what I need to do is that I will first place the object on the platform, right? So this is the platform of the machine. This is the X direction, this is the Y direction, and this is the Z direction. Okay, so first I will place the object on the platform where I want for it to print. Okay, secondly, Secondly, I will orient the part in a way where I will be using the least amount of supports. I can literally put the part in any orientation that I want and the part will still get formed. Okay, but you will kind of have a lot of difficulties in terms of getting certain geometry, certain cross sections according to the direction, according to the orientation that you will place a simple part. Okay, so I will just place this part again. Okay, what we prefer out of this part is to print this part this way. Okay, as we spoke about overhangs before, this overhang is well above 20 degrees to the horizontal, so it does not require supports in this direction. Okay, so the part basically starts printing layer upon layer from the bottom all the way to the tip over here. Okay, so to give you a clarity on this, I'm going to convert my part into cross section. Okay, so as you can see, my software has sliced this entire part into 668 layers. Okay, and as you can see on this top left corner that says layer height, I have mentioned the height of each layer to be 1/5 of an mm or 0.2 of an mm. Okay, and the height of my part, okay, along the XYZ directions are these. Okay, let us just focus on the height. It says about 133.531. Okay, the layer height is 0.2. Okay, so if I divide 133.53 by 0.2, I am going to get about 668. If you get one more or one less, there is a reason for that, and that's to do, with something that is not particularly significant to our discussion right now, so I will skip that. Okay, so tell you how the whole 3D printing process starts. Okay, so you can see that the object starts off as a simple cross section at the first layer, and the height of this layer is about 0.2 mm. You may not be able to see it because 0.2 mm is really, really thin. Okay, so once you kind of understand the color coding over here, we can move on to the next layer, right? So this blue color line, okay, the first blue color line is the path taken by the tool head, okay? And as this is FDM, we are going to basically deposit melted or molten plastic, okay, in this fashion. Now, the first light blue line is nothing but an outer perimeter, kind of just to signify that the printing is going to happen within this, or the printing is going to start within this perimeter. Okay. Now, the red color line is the outer and inner shells of the part, and the green and yellow is nothing but the inside filling of the part. So basically what the machine does is it first draws this outer circle and it draws the inner circle, okay, and then it fills this circle. Okay, once it does this, it forms the next layer, okay, and then it forms the next layer. So we are three layers up now, fourth, fifth, sixth, seventh. And if I were to zoom out a little bit and show you, okay, so this is basically how the object forms layer upon layer. Okay, you can see the cross sections getting formed, and doing this about 668 times, you get the entire object formed. Okay, so this is simply a simulation on the software itself. Okay, so this is exactly how it happens in the machine itself. Okay, and regardless of 3D printing method, whether it be laminated object manufacturing, whether it be selective laser melting, whether it be using powders, using wires, or even simply using photopolymers, the basis or the fundamentals remain the same, that you are always going to process the material in a way that you are going to deposit, or you are going to stack layer upon layer upon layer upon layer. Okay, so finally, just to get back to our presentation, okay, just to get back to our presentation. So what I showed you was opening the printable file in the slicing software. Okay, and on the left side, you may have noticed certain numbers. Okay, now these numbers are analogous to pressing Control P on the PDF file that you have opened. So Control P lets you choose certain settings, right, while printing. So you might want to say you want to print on an A3 sheet or an A4 sheet. You want to print only using black and white ink. You might want to kind of collate, you might want to arrange them in 1, 2, 3. You might want to give the printer certain heads up settings before kind of printing. So the layer slices and tool paths is very analogous to that. So in the case of 3D printing, you are going to kind of signify to the machine what is the height of each layer. You are going to signify whether the infill or the part is going to be hollow, or if it is going to be completely solid, or if it is going to be partly hollow, partly solid. All of these are the parameters that you will be deciding in step 4, or layer slices. And what it means by toolpath is to create this XYZ motion toolpath, which you will be feeding to the machine as the toolpath to be used for processing the powder or processing the material in order to do step number 5, which is very significantly the 3D printing process. All right. So once you have finished all of these 5 steps, one after the other, okay, you have finished these 5 steps successfully, you have a physical 3D object in your hand. Okay. So in order to do this, we have different kinds of slicing softwares. Okay, we are over here talking about step number 3. Okay, Cura, you have 3D slicer, you have simplified 3D, you have slicer. Each of these methods, I mean, each of these slicing software come with their own kind of graphical user interface. They come with their own different kinds of options, different kind of slicing techniques that you can use. Okay, in just to give you an example, one software may simply allow you to just go ahead and slice a part and then use it readily. Another software may allow you to kind of cut a part somewhere, midway, or somewhere 1/3 along the height, so that you can just simply choose to print 2/3 of the object height wise. Okay, so these are the different. It's just a simple example to kind of show or tell you what are the different kinds of differences that separate one slicing software to another. And the slicing software that I showed to you was a very older version of Cura. All right. So Cura, again, I mean, most of these are open source softwares. And if you were to, get down to the day you build your own 3D printer, preferably maybe an FDM 3D printer or maybe any kind of 3D printer, you can always know, and a very comforting thing to know is that these slicing softwares are easy to use, they are free to download, and they come with no licensing restrictions. I mean, at least not all of them do. One or two softwares here and there you can explore. One or two softwares will come with a license. That is because they offer very robust kind of features, but at least entry level softwares like Cura and Slick 3R, they do not exactly come with these licensing methods. So I think this kind of concludes my presentation. This concludes my part of this session on 3D printing. I hope you guys have got new clarity towards the world of 3D printing, towards the science of 3D printing, and ultimately towards the technology of 3D printing. And I hope in my own small way, I've been able to inspire you guys to kind of look into this technology and how it will interest you in the coming future. And I wish you guys all the very best for your future. And I think I will just pass it on to Mr. Vijay now.
Thanks, Santosh. Was really good. Thank you. Can you? Yes, great. So, I really hope you all gained a lot from the session. Santosh was specifically called upon for the session because he has a wide uh, he's done a lot of work in 3D printing, and it's important that when you listen to someone who's done things in 3D printing, it makes a big difference. So thank you, Santosh, and
Thank you so much.
great. That brings us to the end of this workshop. I thank you all for being part of it. It's been a pleasure to host it and look forward to having you soon. Meanwhile, I will share my details in case you want to get back to me anytime you can. These are my details. Uh, do any of you have any doubts that you want clarified? Maybe we can have a short interaction session where we can answer some of your doubts and take it from there. Anything. You can ask us anything. We would be more than happy to answer it.
Hello, sir.
Yes. Yes,
Sir,
Prash.
is any possibility of defect in 3D printing design?
I'm sorry, can you repeat the question, please?
Is any possibility of defect in 3D printing designs?
Santosh, you want to take this?
Pardon me, can you please repeat your question?
Sir, is any possibility of defect in 3D printing design?
Is there any possibility for what exactly?
Defect.
Is there any
Defects
possibility for defects in 3D printing design?
During printing time.
during print. Okay, so you're asking about the defects that will arise out of different 3D printing techniques, correct? Hello? Hello?
Yes, I think that's what he means.
Okay.
Not specifically all, but in general, is there any possibility to get defects due to 3D printing technologies or 3D printing methods?
Okay, to give you clarity on this, since we are processing different materials by different methods, right? Each material can sometimes get over processed. Okay, like you might end up putting more plastic than usual in the case of FDM. You might end up sintering more powder than usual in the case of SLS or SLM, and this will result in certain extra geometry that gets created dimensionally, or it might get created as uh, you know kind of an extra growth, if I may, on the part, which will have to be chipped off manually, or if it is the case of a simple plastic part, you can obviously chip it off or cut it off with a plier. But in the case of metal parts, you might have to use like a grinding method to remove that defect, and this defect could be visual, or it could be metrological wise, it could be a defect on the dimensions. So there are definitely possibilities for over processing the material and introducing defects, as you may have guessed, in different 3D printing methods. And that is where I should kind of tell you that these 3D printing methods require certain degree of skill and experience to master until you can get good hands on to them. Kind of, to give you an example, let us just say you want to 3D print a part which has a 3 mm hole in it. Okay, on your CAD part you might put the hole size to be 3 mm, but when you 3D print this part, using any method, according to the material you're using, this 3 mm could probably shrink down to 2.8, 2.6 mm, or it could even get oversized to 3.2 or 3.3 mm. So considering the kind of material you're working with, and considering the kind of process that you're using, you will either oversize or undersize this hole in a very skillful way to kind of get it to measure 3 mm the first time that you 3D print. So I must highlight to you that you are definitely right that defects can arise, but there is always a method that lies to correct these defects after a print has happened or before a print has happened, and that is purely skill based. I hope I've answered your question.
Sir, how much meshing time requires?
Pardon me?
How much meshing time takes?
How much time it takes to make a part?
No, sir, meshing time design product.
Pardon me? I don't follow you.
Sir, duration of a machining time, sir.
Duration of machining time. You mean after the part has been printed?
Yes, sir.
You don't necessarily have to machine the part. I mean, depends on, suppose you are doing metal 3D printing or SLM or EBM, right? And you end up over processing, as you may have guessed. Okay, are you asking me how much meshing time take? Meshing is, do you mean making the STL? Is that what you mean?
I think so, Santosh, yes.
Okay, all right. So converting a CAD model to an STL very purely depends on your machine's power. To give you a clarity on this, about 15 years ago, it would take about an hour to convert a 3D CAD model into an STL. But systems and computers today are really powerful, and you're able to mesh parts. I mean, mesh your CAD models into an STL within a few minutes. Okay, I think I'll just get back to my example to give you better clarity on this. I mean, Vijay, can I share my screen with
Yes.
them? Okay, so going back to uh, the STL, all right. So in this case, as you can see, when I zoom into the part, right, you can see certain amount of ridges that have been created on this part. And what you can see here is a very high quality mesh that has been created. Okay. And depends on your system. All right. Some systems are able to create a high quality mesh immediately. Some systems may take a few minutes. Depends on the system. Now my system allows me, or my software allows me to kind of change the resolution of my output. Now let me just go to the low, okay, to give you. So as you can see, the same part, right? So the same part over here has formed kind of a very weird geometry on this radius. If you can see that, right? You have a line here and then a line there and then another line. You have about 1, 2, 3, 4, 5 lines, 5 simple lines that are used to create something that looks like a curve, right? So when I 3D print this part, right, I will again have these kind of ridges, and those ridges even get multiplied inside. And since this is a part that moves air from one side to another, I might have some problems with moving air because I am not giving it that smooth cross-sectional flow, right? So I will of course change this to a high resolution, and you can see naturally that more lines have been created in the mesh to accommodate for that curvature. Okay, so to just simply conclude and answer your question again, yes, it does take some time to create these meshes, and they purely depend on the system that you will be using.
Yes, Prashant. To answer your other question, can 3D printing technology be used to fill defects in gas pipelines like the Vizag gas incident that happened? Yes, it is possible. It really depends on what kind of design we are looking at. As long as 3D, as far as 3D printing is concerned, designs can be complicated and we can get it done. We just have to decide on what kind of material we use for it, and based on that, we can select the appropriate technology. 3D printing has the advantage that it can give us parts of different kinds, of different finishes, of different complexity. So yes, we can do that.
Sure. Sir, the SLS machines you explained now, no, sir.
Yes.
Are they similar to conventional machines like laser machining and electrochemical machining, sir?
Not really, because very significantly the uh, laser machining. When you say laser machining, I would naturally guess you're saying laser cutting, right? In that method, you have a laser that is going to subtract material. You basically you have a big sheet and you're going to cut a cross section of the shape or the profile that you want, and that is subtractive in nature, whereas SLS is purely additive in nature because you are constantly adding material to get sintered in the shape that you want. Also, I think I got another question regarding artificial intelligence in 3D printing. I must say that that is a very, very um, significant and very, very important aspect that is taking over. It is we are not there yet. We have not given complete artificial intelligence to 3D printers at this point of time. We have only succeeded, I would say, as a race in giving these machines autonomy to kind of follow instructions, instructions on how to move the printhead between X, Y, and Z directions to create the 3D printed part. I think that in the future, when machines are capable of creating or designing parts themselves, then they will, of course, be able to 3D print the parts itself. But I think we are definitely uh, quite a few years from introducing artificial intelligence to 3D printers at this point of time. Okay, how 3D printing technology influences space technology. Okay, I think this is a very good time to tell you one of the 3D printing techniques that I came across. I mean, I've been doing 3D printing for about 4 or 5 years now, and this is one method that completely blew my mind, and I think it's going to blow your mind as well when I'm trying to answer your question of how 3D printing technology is going to influence space travel and space exploration. Now, we might be able to transport an entire 3D printer. It could be any kind of a 3D printer all the way to, say, a planet like Mars, okay, which is one of the current dreams that humanity is having. Now, I just came across this one person. I'm sorry, it does not occur to my head who this person is. Now, what this person has done is he's created a 3D printer which works very similar to SLS, except this machine, okay, as a material uses sand. Okay, so he put this machine in a desert and he uses sand as powder, and he uses a lens to focus sunlight to sinter the desert sand. Okay, so if you're able to follow, we are talking about 3D printers that can be installed in Mars, and you can simply use the silica or the sand that is found on the surface of Mars as a material, and the power of the sun from the sky to sinter this powder, okay, to form 3D printed parts. And I mean, I'm not sure what is the kind of applications that we might have at the end of the day for this part, but this is definitely what I see, in my opinion, as one of the starts towards, one of the directions towards how 3D printing will definitely change space travel and space exploration in the coming future.
Great. Do you have any more questions?
To make food products to prevent wastage of food. Okay. So a lot of companies, in fact, a lot of startups here in Bangalore itself are definitely exploring 3D printed food. Now, a lot of upscale restaurants are definitely working on 3D printing desserts, 3D printing cookies, 3D printing chocolates, and a lot of them are also kind of doing a lot of work towards 3D printing cells to create, cells that are grown in a lab to 3D print a lot of meats. You must have heard of the whole vegan movement where, they don't want to cause harm to animals in order to rear meat from them. Rather, use a technology like 3D printing to kind of take cells that have been cultured from a lab and use them to 3D print the different kinds of meats. But I mean, of course, I'm not from a biology background. I don't come from a microbiology standpoint of view. But I must highlight to you that 3D printing of meats and 3D printing of desserts is something that is definitely being explored at the moment. And to give you an opinion on wastage, I think that ultimately wastage comes down to how much the consumer consumes the food. But yes, I think because we can create food on demand, very differently from the demand that is getting, I mean, for the demand that we supply currently in the current economical situation. I think that to an extent we will definitely, be able to go in parallelity with the economics of supply and demand to significantly or in a small way definitely reduce wastage. So that is to answer your question. Okay, any upcoming new technology in 3D printing? As I told you, the solar, then you have something called as selective inhibition sintering called SIS, and then you have this SIS method basically uses a technique where you are inhibiting sintering on the cross section of the part and only going to cause I mean, you're going to inhibit sintering along the edges of the part and only center the center cross sections. I mean, kind of to give you an example, imagine you had a cube. Okay, imagine you had a layer of powder that was about 100 mm by 100 mm. Okay, now I will just draw a small square of about 25 mm, 25 mm on the center. Okay, I'm going to draw this square using a liquid called an inhibitor liquid. And then I am going to sinter the powder that is within this 25 by 25 square. And then I will naturally end up sintering even the powder outside of this 25 by 25 square. But because I have an inhibitor liquid between the 25 mm by 25 mm square and the outside powder, okay, over time when I'm going to be stacking layer upon layer, I'm going to have a gap that is being created. Okay, so because I've created a gap, I can simply pull out this 25 by 25 by 25 cube out of the rest of the part. So essentially what I'm doing is I'm creating a part, okay, by inhibiting the outside cross section or the outside perimeter from forming. So this is called SIS method. And then of course there is another method that I came across about a couple of years back where they put an injection and inject it into a vat of liquid, and they introduce some amount of heat or some other kind of a chemical that reacts with the chemical already in the vat and kind of form a 3D printed part that gets suspended inside this vat of liquid. Okay, so I mean, there is really no method. This thing came up, it popped up as a video on social media, it popped up as a video on YouTube, kind of became viral. It was a bubble, and then it went back down. So people are definitely exploring a lot of 3D printing methods. But if you are ever interested in coming up with a 3D printed method or 3D printing method of your own, I would encourage that you first start exploring different kinds of materials and what is the science of bringing this material together. And in order to do so, will you need to be having these materials in the form of a wire? Will you need them in the form of a liquid? Will you need them in the form of a powder? Once you identify that, you identify how you want to put them together. And then once you do this, you build a mechanics around it. And once you've done these three things, you have invented a new form of 3D printing. Okay, how 3D printing can help in agriculture sector? Towards the food and production, right? Since we are 3D printing food, I'm sure we might affect the supply chain of agriculture in the process. But if I'm not mistaken, where 3D printing is helping agriculture is, I would say it's helping agriculture at home. So a lot of people are creating home-based farms that consist of pots which they are mounting onto the walls, and such kind of pots would need different kinds of spaces. Okay, and one home wall is my pot. They can create these pots on demand, put these pots on the wall, and grow a lot of organic fruits and vegetables at home. So, without commenting on the whole agriculture industry as one, I would like to say that 3D printing in its own small way definitely helps you set up an organic agriculture supply chain within the confines of your home. I'm sorry, I just missed a question after that. So the last thing is, okay, I will just. Okay, so to conclude our whole session, now I would like to show you this 3D printed gearbox. All right, so this is a gearbox which goes on a Toyota automobile. Okay, and this is the clutch end and this is the drive end, and it has the entire set of dog gears and dog clutches and etc. And it also has a gear stick which we are actually missing right now. So if you were to see this part, okay, so this part was created on FDM, and looking at it, I am able to do a lot of validation visually. Of course, this is not going to be the real size of the gearbox. The gearbox is probably going to be about 5 to 6 times larger. Okay, but as you may guess, all of these silver parts, they are of course going to be casted. Okay, and to think of it, maybe I can 3D print these parts and use them as patterns for the aluminum casting of the body, and I can use these these dog gears and dog clutches to kind of validate if my gear train is correct. I can always show it to my company, my managers, as to my direction. I mean, this is the solution that I've come up with, the gearbox. What do you guys think? So in all of these methods, what 3D printing helps with you ultimately is two things. One is, of course, validation of your designs. And secondly, and most importantly, it has enabled a lot of us engineers and a lot of us passionate makers to, bring our designs to life within the confines of our homes. And, essentially, I would make a design today and I could have the entire 3D printed assembly with me in a couple of days from now. I do not have to depend on a factory. I do not have to depend on another individual, but I can always have the, part made completely in-house by myself. So this is where I see 3D printing, supporting all of us in the future.
thank you guys. Was a very good workshop. Thank you.